In this video, I'll be talking about electric field due to a uniformly charged sphere. Let us consider you have a charged sphere. Okay, so this is uniformly charged. So when I say this is a uniformly charged sphere, it's just like a solid ball. This solid ball is uniformly charged. Okay, and we are interested in finding out the electric field due to this uniformly charged sphere at point P, which is outside, and at point P, which is inside. But first, we will look for the electric field at a point P, which is outside. Okay, so first what we're going to do, let's say this is your uniformly charged sphere, this one, and at this point P you have to find out the electric field. How are we going to solve it? We're going to solve this one by drawing an imaginary Gaussian surface. This is an imaginary Gaussian surface. Okay, the reason we choose this imaginary Gaussian surface to be spherical, because the integration in the Gauss law will be a lot easier. You can choose any complicated surface, but the calculation will be a lot complicated. So just to make life easier, or just to make the calculation easier, we choose the Gaussians to be the Gaussian surface to be spherically symmetric. So now first thing we're going to do is we're going to find out the charge density. The charge density is the charge per unit volume. And as we know that the total charge we have assumed is the Q. So the total charge is Q, and the volume of a sphere is 4/3 pi RQ. That's the volume. So that is the charge density, the volume charge density. So now as we are interested in finding out the electric field at point P, we have drawn an imaginary Gaussian surface and the radius is R. Okay. Now if you look at any point, at this point P, the electric field is always outward, radially outward. If we choose at this point, then the electric field at this point is again radially outward. At this point it is outward. And the area vector at this point is also outward, perpendicular. So at all points, the electric field and the area vector are always parallel at all points. It's always parallel. Okay. So when they're parallel, then the angle will be 0 degree. That means the cosine theta will be 1. So now we're going to use the Gauss law. This is the Gauss law. This integration tells you the total flux passing through this closed Gaussian surface. Okay. And it doesn't matter where you choose this point. If you have here, or here, the electric field by symmetry is constant, because it is the same distance from this charged sphere. So the electric field E is constant. So and that's the reason we're just taking the electric field out. And then we have dA here. And the angle between electric field and the area vector, as I mentioned before, is 0. So as we know that E dot dA vector is EA times cosine theta, and cosine theta is 0, it will be 1. So we have just dA vector. What does this dA mean? That means the dA, this means the total area of the Gaussian surface, which is 4 pi r square. Now on this part, this tells you the Q enclosed. The Q enclosed by this imaginary Gaussian surface. What is the total charge enclosed by this Gaussian surface? The total charge enclosed by this Gaussian surface is the charge of this sphere, okay, or charge of this solid sphere, which is equal to Q. And the total surface area of the imaginary Gaussian surface is 4 pi r square. So if you now solve for E, what you get is Q over 4 pi epsilon naught r square. Or we know that K is equal to 1 over 4 pi epsilon naught. So the equation becomes KQ over r squared. This is a very familiar equation for the electric field. This is also the electric field due to a point charge. What does that mean? That means for a point which is outside the charged sphere, the entire charge seems to be concentrated at this point. That's how it feels like. So due to a charged sphere, the entire charge, if you assume the entire charge is concentrated at the center, that's how it looks like. The entire charge is just assumed or seems to be concentrated at the center. And K value here is a constant for the air. If you have a different medium, then you have to use the permittivity of that medium. So for a point which lies outside, the entire charge seems to be concentrated at the center, and the electric field is given by this equation. Now we'll talk about the electric field due to the charged sphere when the point P lies inside the sphere. That's the case now we're going to discuss about. So this is the charged sphere, and we are now interested in finding out the electric field at point P, which is inside the charged sphere. This point P is now inside the charged sphere. Okay, so again, what we're going to do, we're going to draw or create an imaginary Gaussian surface. So here we have created an imaginary Gaussian surface through this point P, and a spherical symmetry Gaussian surface. Again, if you look at any point, the electric field and the area vector are always parallel. Okay, so now our task is to find out what is the total charge enclosed by this Gaussian surface. The total charge enclosed by this Gaussian surface is this much charge, because these charges are outside the Gaussian surface. The only charge that are inside is this much charge, whatever charge inside it is. So the total charge enclosed can be found out by multiplying the charge density. What the charge density is? Charge per unit volume. Now if I multiply by the volume of the Gaussian surface, then this gives you the charge enclosed by the Gaussian surface. Okay, and we already have calculated the charge density. If you look here, this is the charge density. This is the charge density, Q over 4 over 3 pi r cube. And the volume of this Gaussian surface is 4 by 3 pi r cube, where r is the radius of the Gaussian surface. If you just solve it, simplify this one, then this is the charge enclosed by the Gaussian surface. Okay, now let's apply the Gauss law. This is the Gauss law. This one tells you the total flux passing through the Gaussian surface, which is equal to Q enclosed divided by the epsilon naught. And here at any point, E is constant. It does not change with the location. If you choose any point here, E at this point or this point or this point or this point is exactly the same because of the spherically symmetry. So E is constant. So we're just taking E as out. Now we are only left with dA. And again, the angle between E and dA is 0 degree. So E vector dot dA vector is basically equal to E times dA times cosine theta, and cosine theta is 0, so it is simply equal to E times dA. Okay, so this is dA vector, dA, and that dA is the area of the Gaussian surface, which is 4 pi r square. And how much is the charge enclosed? This is the charge enclosed, so just plug in this equation this much charge, so just plug in here. Okay, so Q over RQ, this is the amount of charge enclosed, and then we have 1 over epsilon naught. Now if we simplify this equation, we get this equation. And again, in this equation, 1 over 4 pi epsilon naught is the K, which is a constant for the air or vacuum. So, and this value is 9 times 10 to the 9 Newton meter square per coulomb square, and this is for air. So what does this equation tell you? This equation tell you the electric field inside the charge sphere is directly proportional to the r, the radius of the Gaussian surface. That means it increases as you go away from the sphere inside it. That means if you go further and further away, then there will be more and more electric field. If you come closer and closer to the center, the electric field starts decreasing. But if you go move away and away and away, then the electric field starts increasing, and it is maximum onto the surface. That's what it tells you. This is inside the sphere. That means the electric field inside the sphere varies as the r, or r to the power 1. If you look the variation, that's how does the electric field varies inside and outside of a charged sphere. Inside the sphere, it varies as a linear of the radius. At the center of the sphere, at the center, that means here, the total electric field is 0. But now, if we keep moving outward, the electric field starts increasing, and at the surface it is maximum, and outside it decays, or it varies as 1 over r square. To any point outside, it just looks like a point source, and inside the electric field varies as E is directly proportional to R. This is also, if you compare this graph to the variation of the acceleration due to gravity inside the earth, this is exactly how it looks like. Okay, so this is the electric field variation inside and outside the charged sphere shell. So here I will just keep this one so that you can look at all the text here if you need to look at all the text. So you can pause anytime and look at all the text if you need to. Okay, so this is it for the electric field variation inside and outside a charged sphere. If you have any questions,